Hello, everyone. This is Vicente Bolea, and this is the session 6 for our winter seminar. In this section, we will talk about my lab project, which is called Velox Big Data Framework. And concretely about the Velox DFS, which is the distributed file system for our project. So, the reason about choosing this topic, the motivation is I usually make this slide. Is that first of all, it's my honor to introduce to you my projects and my lab projects. It's not only mine. There's many people working on this, and also I think that it's good to have a reference of what a big project looks like. So our project is big. It's maybe around 12,000 lines, maybe 15,000 lines of code so far, but still, I mean, it's not very big, but still, you get some idea of what a complex project looks like and what are the problems, what are the challenge, and so on. And main motivation is that it's my main motivation. It's every day I try to improve and keep adding things. So I want to have a brief introduction of what is it and how was it developed. So we start with this project maybe 4 years and a half ago in 2012, and at that time I was exchange student at UNIST, and it was a summer internship in a laboratory where I took the job to research about different cache techniques. And along my professor, he came up with this idea of distributed cache, which has a ring structure. We're gonna cover about that. And over time, we decide that instead of doing a distributed cache, what if we do a distributed file system? And then after that, what if we use a file system to make a MapReduce framework? So we can compete with Hadoop and Spark, among others. And it went to so we came up with some good ideas, and we tested, and we got very nice performance. In many situations, it was faster than with Spark and Hadoop, and we we had some research papers about that, and we decide to maybe take the path of enterprise. And now we have our own research that is not published at the moment, but it's we're trying to figure out how to make a business out of them. But still, it's academic software. It's open source totally, and it's maybe 60% cook. So it works, but still has some things to be fixed and some things to be added. But it's a good introduction, that's for sure. So the scope of this slides, it's the first part is introduction to DFS. I'm not gonna cover about Velox DFS at first. I'm just gonna explain what it does at DFS, and then about Velo DFS, I'm gonna go through the main difference among its other competitors, and then finally I will make a small uh, performance of how DFS work in one of our clusters. So DFS, what is a DFS? So a DFS, it's a distributed file system. So you can imagine that you have these very large files, maybe like 100 terabytes, and how can you save it? So you need few several computers. So you put many servers, many computers together, and then you divide your file in small parts, blocks is how we call, and you distribute those blocks among those computers. And then you need to figure out how to keep track of the metadata, which is to which block, which file belongs. And that's not enough. You need to now think about how to optimize it. There is a bandwidth, there is the speed of the disk, there is the operating system itself, it has certain buffer cache. So there are many things that you need to consider, and it has been for the past 15 years like a hot topic in computer science research, how to improve. So it's a very hard topic. I mean, many things has been done. There is no more room for trivial solutions. So that's what we're doing nowadays, trying to figure out how to make it faster or more scalable. So at this moment, there is two main distributed file system, which they represent two different kind of distributed file system. So in one side we have HDFS, which is our main competitor. It's a Hadoop distributed file system. So Hadoop is famous for the MapReduce engine, but inside the Hadoop, its distributed file system, which it's very similar to ours, and it's basically divide the files into blocks. And then opposite to Hadoop, we have Cassandra file system, which works more like a database, more like a key value storage. So instead of storing like a large blocks in each of the server, it stores a key value as a hash table. So let's start with Hadoop HDFS. So that's how it works. I like this very simple diagram. So Hadoop has two kind of servers. Some of them they are data nodes, so they only store data. They don't know anything about the other guys, so they just receive blocks and requests and they just reply. And they have a name node, which is like a master. So the name node is the server that you connect as a client, while the data nodes you don't connect directly. You need to have a permission, at least it's how they call it, from name node to actually request some data from them. And the way that it manage, so this is the idea about the blocks. So you have this very large file, and then the large file you divide in blocks, and then you send each of the blocks to the nodes. There are many ways, it's depending on the scheduler. So one key feature, it's fault tolerance. So if you have one computer and you have good hardware, maybe the computer will not fail for 2 years, depends, or for 4 years hard disk. But if you have 1,000 or 10,000 computer, the probability of disk failure, it's way higher. As I remember from some of the papers about this, I heard uh every week for like 1,000 nodes they have like some sort of disk failure. So it's something that always happen, and a good distributed file system need to keep track and handle the situation quite very well, because that's one of the main thing about distributed file system. So the way that Hadoop handle that situation is by using replicas. So replica is pretty much, if block one it's in this node, then it make a copy and then it's into node 2. So if node 1 dies, node 2 still have the data. So normal replication number is 3. We in our distributed file system we follow the same replication number. And yeah, so there is another problem. Even though we might have many data nodes, actually HDFS, it comes from the Google distributed file system, same architecture, and they have the same problem. If name node fails, then it's quite a problem. So they had this secondary name node that it's always on in case this one fails. But you might see that if you scale up the name of data nodes, maybe it's a big bottleneck here. And no matter also to say about how smooth the transition from this first name node to the secondary name node goes. So there's a big problem there, and there is an open door for research there, and some idea we already came up. At the moment, not published, but well, maybe in the future. So yeah, that's one big problem about this one, and the main reason is it's because it's centralized. If it was decentralized, then we would be talking about different thing. But because it's centralized, we always had this master thing, a master problem. And as Google said in their Google File System paper, the reason of choosing this architecture, it was not to make it efficient or to make it uh, fault tolerant. It was to make it simple to code because it's a complicated software. It's not a trivial piece of software. So that was the reason. And on the other hand, we have Cassandra, which differs quite a lot from our distributed file system. So for each file, it divides in blocks, and then the blocks are again divided by subblocks. So each blocks they have information about where the subblocks are, and then the subblocks are distributed among the nodes in a very balanced manner. So it's a key value store. That's how we call it. And then you can access that information of the blocks using query, similar to SQL. And it might look like a very big database, and that's actually how they use it. So even though it's a distributed file system, Cassandra is actually a distributed database, but the file system that they use is to store that database information. So it's a distributed file system as well. So yeah, so that's those two ones that I wanted to introduce, Hadoop and Cassandra. And now let's move to our Velox DFS. Check the time. Okay, good. So our Velox DFS, it's very similar the way that we separate in blocks to HDFS or Google File System or Android File System, but we are totally decentralized. So we don't have a master. As you can see, all of them are connected in a ring manner, but there is no master. So the ring manner is more to, how can I say, we couldn't make a mesh, but if you think about it, it's keep it simple, right? So the idea is that yeah, same thing. Yeah, it's important to say that we also plan to support key value content as in Cassandra, but that's a part of the research that it's in a very early stage. It's just important to say, but yeah. So the way that we know we support this distributed file system is that we have a distributed hash table, which tells you always aesthetically to which file we have which node. Sorry, which node has which file. So if we insert foo.text, then it will tell you it's in the node 7. So now we know that this node is the number 7, is the file leader for the foo.txt. So it will have information about where are the blocks located. And the title blocks. So when we insert a block, we ask the file leader, and then the file leader will tell you, okay, block 1 should be go in this node, block 2 in this node, block 3 in this node, and then we insert block 1 at first. And once we insert it, we also need to support replication for fault tolerance. As I explained before, it's a very important feature that we cannot miss it. So yeah, and the way that we replicate is that we always use the neighbor nodes. So in that way, we can refer to the replicas very quickly. So it has some problem with the balance, but we solve it by using other techniques. By distributing the balance in a different manner. So yeah, that's how it is for the writes. So file leader knows where to put the blocks, and we can aesthetically know where is the file leader for each file. So for every file, there will be a different file leader. So if we had maybe 12 files, maybe each of them can be a file leader of any of them. So it's that's why it's decentralized. Instead of having one master, we have like as much masters as files we have, but all of them are decentralized. And the master replicates its metadata information in the neighbor nodes as well. So in that manner, we can always recover from a failure. So we can recover the blocks and the metadata. So what about read? So read is even easier than write. So when we read, we know we need to ask the file leader, and then the file leader will tell you which nodes they have the blocks, and then you read from the blocks. So one optimization that we having now is that we have, let's say, not sorry, this node has block 0, block 1, block 2. So by the time that you start reading from this one, they will cache the other ones. So in that manner, uh, even this one is gonna be slow, but these two others is gonna go faster. So that's a kind of primitive optimization, but it's actually the best we can get for the read operation. For write operation, there are many other things like lazy, put, or other possible optimization. But for read, that's what we found, and it's good. So how does it look like? As usual, it's a term. Our interface is a command line. It's a command, and we support many commands, as you might see. Still, we wanna keep adding more, like rename or uh, not sure. But anyways, that's what we support so far, and at some point it's quite stable. Our DFS, and you can download anytime. It's open source, as I said. So this is the wrap up the conclusion for DFS. Velox DFS is a decentralized distributed file system. There is no master node, so having that thing, we can scale faster. We can go from 10 nodes to 10,000 nodes very quickly. Uh, the files leader, they are, we know where they are using our DHT. We support fault. We can recover from fault tolerance using our replicas. Uh, we support content-based store, which is the block base. At the moment, not key value. And we have interface for the shell. It's a command line. For C++, it's our native. For Java, recently we added, and for Python. It's not written there because it's a primitive support, but we support the DFS pretty much. Not all of the functions, but append, get, put. We don't have partial gets, for example. That's why. And I would like to show you the GitHub repository. So here is it. This is the README file. There is an instruction to how to install and how to configure. Configure is a hard part for this project, and installation as well because it requires Boost library and it requires higher version than 1.54. And yeah, so that's it. So the code is, yeah, it's pretty much like this. Maybe I would like to show you the interface. It's fairly simple, right? And we got some examples here. No, we don't get it. We had the documentation in these websites. It's pretty useful if you want to contribute. you got this nice graph of how all the class diagram it is, and yeah, that's all the classes we're using. Wait. So if you want to install, you should check out the configuration file reference. There are quite many options you need to add. So yeah, it's better to copy and paste and just personalize for you. Yes. And yeah, we use pull requests for our projects. We use it pretty much and quite often. I mean, last time was 7 days ago, 8 days ago. So yeah. And one very important thing that I need to mention here. Okay, let me see if I have time. Okay, let's. Yeah, I have time. So, we don't include in Velox DFS launcher, and that's important. So the reason is that we want we don't want to force to user to use any launcher. They can use maybe systemd or initd or whatever they want to use. But in our case, for our development, we use a launcher called Eclipsed. So it's this one, and well, there is no documentation, but I can. I'm gonna show you in the next session how it works. So you can launch, relaunch, debug. Many things you can do with this thing. It's like a that kind of tool that's very useful, right? So that's what we use for development. So anytime we need a feature, we just add it right away. So yeah, it's a Rabbit gem, so you can install using gem install. And another important thing to say that's while Velox DFS focus on it's a distributed file system. We have Velox MR, which is the MapReduce framework, and we also it's open source, same as Velox DFS, and at the moment it supports iterative workflow and Python. At the same time, C++, which is native for it. So this is a repository. We can see some of the examples here. Targets, like a word count, like this, and k-means. K-means. We can run k-means algorithms using iterative workflow in C++ actually, and it's really nice because you have a Spark which use Python and Java, and they have some limitations that we don't have. We can really work at the very very CPU level, and that's really nice. So yeah, the k-means call is very hard to follow, but anyway, it's possible. That's the really big point. It's hard to follow because our interface is very primitive at the moment, but we need to work on that. Yeah, this is another very simple app. I can't remember what it does. It's a counting app to count how many characters you have, something like that. So yeah, that's our framework overall, and as you might see, this two release here is pretty new. This MapReduce DFL is older, and yeah, I want to show you what many people work here. It's contributors. So yeah, all this guy we have working here. As I'm the main maintainer, and why they came here? Well, so yeah, so there's quite many code, lines of code as you might see. Yeah. Well, 1 million. Oh wow. Okay. So yeah, I will continue the seminar in a few minutes, and I will explain you how to use Velox DFS. Hey guys, I'm back in the seminar. So now I'm gonna show you how to use the Velox distributed file system, Velox DFS. So I have a terminal here with I'm in a cluster of 8 servers. All of them are running Ubuntu 14 1404, and in here I have many files, and you can see maybe, yeah, so there's 1 gigabyte, 5 gigabytes, and so on. And sharing this computer, I mean, with many people, so it's cannot, it maybe not fast. This one is a development cluster, so it's not a performance show. So the first thing that we will do with um, Velox DFS, I'm gonna go through the commands very quickly. So we're gonna use this DFS for talking to the framework, and we're gonna use Eclipse D to actually control the framework in the sense that, so okay, so we can launch it, close it, restarts, get a status, and then kill it. If the gentle close doesn't work, then yeah, it's a developer tool, so we need to kill it. And then as for the MapReduce, we can submit applications. So we're gonna cover about this a little bit later. And then we can compile from here. And yeah, we can use it for debugging. It's a pretty useful tool. So this seminar might be also for developers of Velox distributed file system. So I'm gonna cover about this as well. And yeah, this one means, so we have 3 options here, and this option means that you want to relaunch, restart, but with one of the nodes in debug mode. So you launch, you invoke a GDB session in a remote server, and then in here it's already running the distributed file system, but you want to attach GDB to one of the nodes. While here, you want to launch all the nodes normally, but one of them indicated with N, you want to launch it by yourself. You maybe want to add some options, that specific one, or it's up to you. And yeah, rest of them are quite not unimportant. So let's see the status of the this Eclipse and Velox DFS. So status. So yeah, we have all of those machines that are working. It's a peer-to-peer network. Don't forget about this decentralizer. This role thing, it's well, it's a legacy thing that we didn't change, but it doesn't mean anything. All of them are worker, of course, and yeah, all of them are running. So if I close it, yeah, all of them are stopped, and then I can launch it. And yeah, now it should be all of them running. Okay, good. So now we cover about the Eclipse D. As I say, it's a small but simple tool. And now let's see about the DFS command. So DFS, we have all these functions. So I'm not gonna cover about all of them. I'm gonna focus on until here, I think, because rest of them you can imagine. It's harder to make an example, but you can imagine what is it. So at this moment, let's see what we got. So we had this file. The file leader it's in this node, which is number 3, number 2, and then it's divided in 8 blocks. The size. Okay, wait. I can use this flag. The file is 1 GB, and its hash key is this one. So it's a good information. And then if I want to see in which, so it doesn't have replication level at this moment. So if we want to see in which block are, in which node are which block, we have this other comment. Yeah, it's not shown in the normal information because it's what we use. We need to show it. So yeah, 1 GB AA. So yeah, that's what we get. So block 0, it's on this one and block. So as you can see, our file system distributed quite balanced. There is no repetition. So that's one of the features we focus quite a lot actually. How to always make a balance, and that's important feature. And it's such a good thing because it's decentralized. So well, anyways, so let's remove everything, and now we have nothing. Let me check the time. So now let's put some file. So we have DFS, puts, and maybe 1 GB AA again. And yeah, let it wait. Okay, we're done. So it took a little bit long time, but as I said, we're sharing this cluster with many people. But yeah, it's not important. We already raised the performance many times. So now we have the file again back there, and we can download the file. So DFS gets 1 GB AA. So you can imagine what's happening right now. So there is many blocks, so it's going one by one. One, one. There's many servers hosting different blocks, and then it's going to one server, requesting the block, getting the block, another server, getting. So we explain how it happened. So it's interesting because how many computers are working together, right? So this system, it's what all these clouds computing storage in this case is about. It's what a Dropbox probably is using. It's what a Google is using. So yeah, Google is very similarly software, Google file system. So yeah, I think it's a good introduction for you about distributed file systems. But yeah, let's wait this one. So I might want to use a small file so I can show you. So yeah, we had this 1 GB. Yeah, 1 GB, same file is there. And maybe I can introduce a small file like this. So cat is quite, I mean, same as a cat at the in the command line. So normally for MapReduce jobs, it can pretty useful because the output file is normally very small. So yeah, it's important to mention. And then obviously, in the same way, you can remove files, and yeah, you can remove big files. Very fast removing, right? And yeah, so that's it for the Velox TFS. And one thing I want to show you, it's about the MapReduce. So we also have an interface, and the interface it's also over in Python. So we can do things like this. Well, this one is for the MapReduce. So we can do like this. We can create a file. We can open it, and then we can append contents to the files. We can load it to the client, and then we can prepare to the file datasets. So dataset it's like a group of files because when you want to run map and reduce, you might want to run in many files. So we have this datasets thing. So and then you can run Python mappers or Python reducers in there. It doesn't make a lot of sense to do like this, but I mean we use it for debugging. So I just want to show you how it looks like. Also the word count.cc, maybe it's more, yeah, like this. So we have a reducer that looks like this, and our mapper that looks like this, and then we just run it. So we pen the file, we run map and reduce, and that's what we get. And the thing I want to show to you, oh yeah, it's the Python version. So yeah, you define your map, you define your reducer, and then you can call MapReduce like this. You can also do like put some file before that or whatever you want. In our case, for the MapReduce, already the first uh, the first parameter means the file for the input, and this one is for the output. So one important thing here is that for our support for iterative MapReduce in Python is very primitive. That's why I said that we don't really support at the moment. We cannot support it, but we need to work more on that. So that's how we support iterative MapReduce. See if I can give you some examples. Maybe I'm running out of time. 15 minutes. So yeah, this for the for the MapReduce part. Sorry for someone was calling. And so yeah, these are called, and so that's one very quickly thing I want to show it to you before I finish this part. Uh, I want to show you how I work in these projects. So I always have like this. Can you see? So this one I use. So I use a sniffer to see what's going on in the network, and I follow the logs. So if I do like this, I can see, oh, those messages came like that. and I can see the logs what's happened. So it's pretty useful. And one more thing to show to you is a configuration file. So in that, this is really important thing. So to improve performance, you might want to add more thread to the thread pool. It's in this flag. And for the cache, maybe, yeah, not to worry about that at the moment. Also, the block size is very important. It's bytes. So you need to find the block size that actually match your hardware. And the buffer for the network. And this one is maybe important as well. By default, it's you can use XML. Uh, it's very slow. It's good for debugging. You might see why. So if I use XML, look what's happened. So I need to restart whenever I change the configuration file. So if I do ls, I can see what are the message, control message. So it's very powerful for debugging. That's why I think that's important to mention. So I use in daily basis, and yeah, that's pretty much. So yeah, that's pretty much. And then the repository you had, as I said before, MR and DFS, and you can start and follow the the development of Velox Big Data Framework. And we're quite active with many people there. So if you have any question or something, we will very happy to contact you and help you with anything. So before I finish this seminar, I would like to thank Tukyon, who is my lab mate, and he helped me with some of the uh, these graphs and these things. And yeah, that's it's been a lot of time working on this one, and I'm very happy of the progress we have done so far. And the continuation, I'm gonna add a video about how to use the MapReduce in our Velox software. So thank you so much. I will make a new seminar about a sample project where I'm gonna show how I normally confront small projects, and within 30 minutes I'm gonna write a sample application using all of the tools and techniques that I described before. So after this one, we're gonna have a video of the Velox MR in action. Thank you.